Hello, welcome back. This is Physics 102A, homework solutions for Chapter 12 on temperature, thermal expansion, and ideal gases. We start with number 17. It says, starting at room temperature, increasing a steel rod's length by 1% requires a temperature of about what? And this book gives multiple choices. So let's write down the given information. We have our initial temperature, room temperature 20 degrees Celsius, and we need for steel the coefficient of length expansion, which is alpha 1.2 times 10 to the negative 5. And because it says we're increasing the length by 1%, we can write it like this, that the change in length over the initial length is going to be 1% or 0.01. We want to know the temperature. And when we set it up this way, we can see that it fits into the way the equation that the book gives, that delta L over L naught equals alpha delta T. And let's solve this for delta T. So delta T is 1 over alpha times the fraction of length change. And so we'll do 1 over alpha times that 0.01. And what we get is, when we plug in the numbers, delta T is 833.3 Celsius degrees. And let's think about the left-hand side. Delta T, that means change in temperature, final minus initial. And the question is asking, what is the final temperature? So let's add T naught to both sides. And we have final temperature is the original temperature, 20 degrees Celsius plus 833 Celsius degrees, and we get 853 degrees Celsius. We look at the multiple choices, and B, 850 degrees, is the appropriate answer. Number 18, heating an aluminum block from 20 degrees to 440 degrees Celsius causes its density to change by about what percent? It's asking about the density changing. Now we have an equation for volume changing, so we know that density is related to volume. I've written down all the given information. Here is delta T, 440 minus 20, which is 420 Celsius degrees. We'll need the volume coefficient of expansion for aluminum, 7.2 times 10 to the negative 5. And we want to know what is the density increase. And the multiple choices give it as a percentage. So we're going to think of it in terms of a ratio, the new density over the old density. So rho over rho naught. And we know that density is mass divided by volume. So the final rho, the final density, is mass divided by the new volume, divided by the original density. So we're going to divide by mass over volume naught. And dividing by the fraction means multiplying by its reciprocal, as you can see here. The mass, because it stays the same, that divides out, and we're left with the original volume over the final volume. So the new density over old density is the old volume over the new volume. And we've got the old volume, and in the denominator, the new volume is original volume times 1 plus beta times delta T. So I'm using this formula that's up here. This formula, I don't think it was specifically given in the book, but this is what I've given in class. And so it's good to use this form of it. And now let's plug everything in. Well, actually, before we do, we can see that the old volume divides out, leaving a 1 in this numerator. So it's 1 over 1 plus beta delta T. And here we have the reciprocal of 1 plus beta delta T. And we can plug in all the values given. And we work it out, and it comes out to be 0.97. So what this is telling us is that the new density over the old density is 97%, or the new density is 97% of the old density. And now we go back and read, what did the question ask? It causes its density to decrease by about how much? Well, if it's 97% of what it used to be, then it's a 3% decrease. Number 20, an ideal gas at 20 degrees Celsius and 10 to the 5th pascals pressure occupies a constant volume container. If its temperature increases to 80 degrees Celsius, the pressure becomes what? All right, it's going from 20 degrees Celsius to 80 degrees Celsius. And remember, that is not a quadrupling of temperature because it's on the Celsius scale. We need to get it in Kelvin. So add 273.15 to all those Celsius temperatures and you get Kelvin temperatures. I've written it out as T0 equals 293 Kelvin, P0 is 10 to the 5th pascals, T1 is 353 Kelvin, and P1 is what? And we'll start with the ideal gas law, PV equals nRT, and we'll use the technique where we algebraically move everything that is constant off to the right. We'll keep things that are changing to the left, things that are constant to the right. So going through the algebra, you get P over T equals nR over V. So P over T is constant, and we don't care what the constant is. It's just important to know that it is constant. And with that in mind, we'll say P1 over T1 equals P0 over T0 and solve for whatever we need to solve for, P1. So we get P1 is P0 times T1 over T0. So you can see the new pressure is based on the old pressure times the ratio of the new temperature to the old temperature. And we get 1.2 times 10 to the 5th pascals. Number 37, a 50.00 meter long steel measuring tape is calibrated for use at 20.0 degrees Celsius. How long is this tape under the following conditions? A hot day with temperature 32 degrees Celsius, and B, a cold day with temperature negative 10 degrees Celsius. I've written out the given information. And we're going to start with on a day that is 32 degrees Celsius. So the new length is old length times 1 plus alpha delta T. We'll plug in all the values. Here's the alpha for steel is 1.2 times 10 to the negative 5. Change in temperature is final minus initial, so 32 minus 20. And we get 50.0072 meters. So this 50-meter long tape on a hot day has actually expanded by 7 millimeters. Part B, on a cold day, it's going to shrink a little. We'll use the same equation, but now final temperature minus initial temperature is negative 10 minus 20. That's going to be negative 30, so it's going to make this part go negative. And we end up with a length of 49.982 meters. Number 44. A beaker with a capacity of exactly 100 milliliters contains 99.8 milliliters of ethanol at 25 degrees Celsius. If its temperature rises, at what temperature will it overflow? Ignore expansion of the beaker itself. So we're just going to take into account the ethanol expanding to beyond 100 milliliters. We need the volume expansion coefficient for ethanol. We look it up in the book, 7.5 times 10 to the negative 4. Original volume is 99.8 milliliters at a temperature of 25 degrees Celsius. So at what temperature will V exceed 100 milliliters? Let's use this equation right here. Volume equals original volume plus or times 1 plus beta times delta T. And we'll solve for temperature. So I go through the algebra. I've, in this step, divided by V0, then subtracted 1, leaving beta delta T. I then divide by beta, leaving delta T, and I've switched left and right hand sides. And so then we get delta T is 1 over beta, I'm plugging in the numbers here, times new volume, which is 100 milliliters, divided by 99.8 milliliters, minus 1. So we're getting a change in temperature of 2.67 Celsius degrees. The question is asking, at what temperature does this occur? So the final temperature is the original 25 degrees Celsius plus the rise of 2.67 Celsius degrees. So we get 27.7 degrees Celsius. Another way to do number 44 is to use this equation that's given in the book. Delta V over the original volume is beta delta T. Solve that for delta T, and so we get 1 over beta times change in volume over original volume. Now, the change in volume is going to be 0.2 milliliters because it starts at 99.8 and goes up to 100, so 0.2 milliliters. And then we get the same result, 2.67 Celsius degrees. And then we add that to the original temperature, and we get 27.7 degrees. Number 49, find the mass of these 4 different things. And so it starts with 1 mole of argon. Well, we need to look up the molar mass of argon that's in a periodic table, such as the one in the back of your book. And the molar mass we read is 39.95 grams per mole. And so that's it. 1 mole is 39.95 grams. Part B, 0.25 moles of carbon dioxide. We look up in the periodic table, we see carbon is 12.01 grams per mole, oxygen is 16 grams per mole, and we're going to add those together. We've got 1 carbon plus 2 oxygens, and so 12.01 plus 2 times 16, we get 44.01 grams per mole. That's the molar mass of carbon dioxide. We're going to take that many grams per mole, multiply it by 0.25 moles. You see we handle this like we do a unit conversion. The moles divide out and we're left with grams, so 11 grams. Part C, 2.6 moles of neon. In the periodic table, it says neon is 20.18 grams per mole, and we're going to multiply that by 2.6 moles and get 52.47 grams. And finally, D, 1.5 moles of uranium hexafluoride. Uranium is 238.03 grams per mole. Fluorine is 19 grams per mole. And this molecule has 1 uranium and 6 fluorines. So we add those up and we get 352.03 grams per mole for uranium hexafluoride. Then, that's for 1 mole. We want 1.5 moles, so multiply that by 1.5. And we get 528 grams. Number 51. How many air molecules are in a classroom measuring 8 meters by 7 meters by 2.8 meters, assuming 1 atmosphere pressure and a temperature of 22 degrees Celsius? All right, this is the ideal gas law. And it's asking how many molecules of air. So we have a choice to use PV equals nRT, little n RT, or PV equals nKT. And the difference is little n in PV equals nRT relates to the number of moles. Big N in PV equals nKT is the number of molecules. So we're going to use this version. We need the volume, so multiply length times width times height of the room. We need the pressure. We need all this in MKS units, so 1 atmosphere is 1.013 times 10 to the 5th pascals. Temperature, we need that in Kelvin, so add 273.15 and we get 295.15 Kelvin. The ideal gas law, PV equals nKT, we solve for N, PV over KT, and K is the Boltzmann constant. You can find that in the front flap of your book. 1.38 times 10 to the negative 3 joules per Kelvin. Plug in all the other values and we get 3.9 times 10 to the 27th power molecules of air in the classroom. Number 53, a spherical balloon with radius 10 centimeters contains a gas at 1.05 atmospheres pressure. The balloon is put into a hyperbaric chamber at 1.75 atmospheres. Assume that the balloon's temperature remains constant. A, does the balloon's size increase or decrease? And B, compute its new radius. All right, so we have this spherical balloon and we put it into a higher pressure environment. And you can just imagine the higher pressure environment is going to squeeze down on the balloon until the pressure inside and outside reach equilibrium. So it's going to squeeze it down until the pressure on the inside pushing out is 1.75 atmospheres. And if you picture that, you can imagine it will decrease inside. It's getting squished down. Well, let's write out the given information. The original radius, R0, is 10 centimeters, and I've called that 0.100 meters. It might not be necessary to convert it to MKS units, but I did it anyway, and we want to know the final radius. The original pressure is 1.05 atmospheres. The final pressure, again, because it's in a 1.75 atmosphere environment, it will squeeze down until it's got the same pressure on the inside. So the pressure on the inside becomes 1.75 atmospheres. We start with the ideal gas law, PV equals nRT. N, R, and T are constant, so we have PV is constant. We see this inverse relationship between pressure and volume. So as the pressure rises, the volume decreases. Now let's actually solve for the final size. We'll say, since PV is constant, that P1 V1 equals P0 V0. Solve for V1, and that is V0 P0 over P1. Now, the question is not asking for the volume, it's asking for the new radius. So let's turn volume into the radius. It's a sphere, so 4/3 pi r1 cubed. And on the other side of the equation, 4/3 pi r0 cubed. And we will solve for r1. And notice how things divide out. 4/3 and pi divide out of the equation. And we're left with r1 cubed is r0 cubed times p0 over p1. We can simplify that by taking the cube root of both sides of the equation. We get r1 is r0 times the cube root of p0 over p1. So r1 is the original radius of 10 centimeters times the cube root of 1.05 atmospheres over 1.75 atmospheres. Calculators often do not have cube root keys, or sometimes if there's a cube root function, it's a little tedious to get to it. And so an easy way to do cube root in the calculator is just to put it to the 1/3 power. So the exponent of 1/3 is usually an easier way to get there. And you get a smaller radius of 8.43 centimeters. Number 60. A compressed air cylinder stands 100 centimeters tall and has an internal diameter of 20 centimeters. At room temperature, its pressure is 180 atmospheres. How many moles of air are in the cylinder? What volume would this air occupy at room temperature and 1 atmosphere of pressure? So you can imagine if all this air were to escape, and assuming it would go to 1 atmosphere, it would take up much more space. And we're going to figure that out. Here's the given information, the height and the radius. It said the diameter is 20 centimeters. That means the radius is 10 centimeters. Pressure is 180 atmospheres. Temperature, let's get that into Kelvin, 293.15 Kelvin. We want to know how many moles. So N equals how many moles. Let's solve the ideal gas law. PV equals nRT. N equals PV over RT. Now, V is volume, and this is a cylinder, so that's pi r squared times H. We have to be very careful about the units here, and so if we're doing it in centimeters, we can keep that. So I've done it in centimeters, and it's 31,416 cubic centimeters. I've also done, I've just left it as 180 atmospheres for the pressure. Notice I didn't plug in an R value yet. We'll talk about that. And the temperature. Now, we need to think about the units we're going to use. We can convert the volume either to liters or cubic meters. Now, the choice would lead us to what R value we're going to use. If we choose to go with liters, then, as this is what I've done in the green ink, then we'll need R equals 0.08205 liters atmospheres per mole Kelvin. However, if we choose to turn this into cubic meters, we're going the MKS route, then R is 8.314 joules per Kelvin mole. And it doesn't matter which way you go, just pick one. So here on this page with the green ink, I've done it using liters, and then on the next page, I'll show you doing it the MKS route. So 31,416 cubic meters. It's good to know that a cubic meter is a milliliter. They're the same thing. So that's 31,416 milliliters, which then is 31.416 liters. So I'll plug that in, and I'll use the R value that makes it all work out well. So you see atmospheres, liters, and Kelvin. I'm using the R value of 0.08205, that is liters atmospheres per mole Kelvin, and it'll make all this turn into moles, so 235.10 moles. Now, here is the same problem, but turning it into MKS units. Volume of 31.416 liters is that times 10 to the negative 3 cubic meters. We also would need to turn pressure into pascals. So multiply that 180 by 1.013 times 10 to the 5th pascals. And so now we have our pressure in pascals, our cubic meters, our MKS R value of 8.314 joules per Kelvin mole, and then temperature, and you get, again, the same result, 235 moles. Number 60 continues with part B. What volume would this air occupy at room temperature and 1 atmosphere pressure? So we have volume equals nRT over P. And we solved in part A the number of moles, 235, times R times Kelvin divided by 1 atmosphere, which I've turned into pascals. So all of this is MKS units, and we get 5.65 cubic meters. Now, another way to do that, as I've done in the green ink here, is to compare the original quantities with the final quantities. So PV equals nRT. We get the constants to one side. They're already over there, N, R, and T, leaving PV, the values that change, equals constant. So P1 V1 equals P0 V0. Solve it for the new volume. V1 equals P0 over P1 times V0. So we have the pressures 180 atmospheres over 1 atmosphere. Whatever units you use will divide out, so it's just a 180 to 1 ratio, times the original volume. And the question didn't specify what type of units, liters, cubic meters, cubic centimeters. I just left it in liters, so 31.416 liters, and you get 5655 liters, which is also 5.65 cubic meters, which is the result that I got up here. Number 75 says an ideal gas is maintained at 1 atmosphere pressure. By what percentage does the density of the gas change from a cold day, negative 10 degrees, to a hot day, 32 degrees? So it's asking by what percentage does density change? Whenever something's asking by what percentage does it change, we're going to set up a ratio of the new to the old. So we're doing rho 1 over rho 0. By the way, I've written all the given information. We're going to need temperature in kelvins. So rho 1 over rho 0, we had something like this in a previous problem in this video. Mass over volume 1 times volume 0 over mass. The masses divide out, and so the ratio of the densities new to old is the ratio of the volumes old to new. Now, we'll come back to that. PV equals nRT, and in this case, temperature is changing, volume is changing, and it says the gas is maintained at 1 atmosphere, so pressure remains constant, which means that V over T is constant. And we'll set that up. V0 over T0 is V1 over T1. Do a little changing around. V0 over V1 equals T0 over T1 with some algebra. Now, why am I doing that? Because up here, V naught over V1 is what I'm going after. This is going to give us the answer of the ratio of the densities. So V naught over V1 is T naught over T1. Plug in those temperatures in Kelvin, and we get 0.86236. That is the ratio. So the new density to the old density ratio is 0.86236, or we can say the new density is 86.24% of the old density. We go back and read, what did the question ask? It asked, by what percentage does the density change? So if it's 86.2% of what it used to be, then it has decreased by 13.8%. Number 76. Venus's average temperature is 730 Kelvin, and its pressure is 100 times that of Earth. Find the volume of 1 mole of Venus's atmosphere. So we have the temperature, we have the pressure in MKS units, so we're going to multiply, if 1 atmosphere is 1.013 times 10 to the 5th pascals, we multiply that by 100, and it's 1.013 times 10 to the 7th pascals. And the question is asking about 1 mole. The question is asking what is the volume. So PV equals nRT. We solve that for V equals nRT over P. 1 mole times, now there's the choice of R to make, and we can choose to do this in MKS units or liters atmospheres per mole Kelvin. I've done them both ways, and so in the black ink I've gone with this 0.08205 liters atmospheres per mole Kelvin, which means I'm dealing in liters and atmospheres. Multiply by the temperature, divide by 100 atmospheres, and we get a volume of 0.60 liters. Now in the blue ink down here, I've done it in MKS units, so we're going to end up with cubic meters. nRT over P, we have 1 mole. R is 8.314 joules per mole Kelvin. We have the temperature of 730 Kelvin. And now we're going to use pascals, 1.013 times 10 to the 7th pascals. And we get 6 times 10 to the negative 4 cubic meters. And that is the same as what we got up here, 0.6 liters. Number 83, involving medical oxygen. The medical oxygen cylinder supplies 165 liters of oxygen gas at 20 degrees Celsius and 1 atmosphere pressure. Internally, the cylinder measures 28 centimeters high by a 6.8 centimeter in diameter. What's the pressure in a full M6 cylinder at 20 degrees Celsius? So we're talking about highly compressed oxygen. We expect it's going to be much more than 1 atmosphere. We had a similar problem earlier in this video. It was number 60 that involved a compressed air cylinder that was at 180 atmospheres. So we can expect that it might be pretty high in atmospheres. Well, let's take from the paragraph the given information. It says it supplies, meaning when it comes out, it's a volume of 165 liters. So V1 is 165 liters at a temperature of 293.15 Kelvin. That's 20 degrees Celsius. And a pressure of 1 atmosphere. So that's P1. And the question is asking what is the pressure inside the cylinder. So we'll call that P naught. We're going to need to know what the volume is inside the cylinder. It gives us the dimensions. Volume of a cylinder, that's going to be V naught, is pi r squared times h. So pi times the radius of 3.4 centimeters, square it, times the height of 28 centimeters, and we get 1016.87 cubic centimeters. Now, cubic centimeters are the same thing as milliliters. And so we can turn that into 1.01687 liters. And I turn that into liters as opposed to cubic meters because the information given for volume V1 is in liters also. So let's get the initial volume in liters as well. We take the ideal gas law, PV equals nRT. We have the constant quantities to the right, and that's the number of moles, the gas constant, and the temperature, leaving the changing quantities on the left. So PV equals constant. That gives us P naught V naught equals P1 V1. We're going to solve for P naught. So P naught is P1 times V1 over V naught. And we've got 1 atmosphere for the new pressure. And we have our ratio of the volumes, so 165 liters over 1.01687 liters. And we end up with an answer of 162.3 atmospheres. That is the end of the Chapter 12 homework. Have a great day.